This is a simulation of neuroevolution using artificial neural networks and a genetic algorithm. Um, the creatures in the simulation are given three inputs, or sorry, are given um, have three outputs, which are to turn left, to turn right, to move forward, and they have inputs um, corresponding to a left and right eye, which have a limited um, field of view, and they also receive feedback from the actuator neurons. Um, so this is after almost 1 million steps. Um, the lifetime of a newly spawned creature is 1,000 steps. However, um, the lifetime may be increased if they manage to collect food. So um, over time, you see that several phenotypes have developed which allow um, the creatures to be better at collecting food and staying alive. Um, there is both asexual and sexual reproduction algorithms implemented. The sexual reproduction algorithm selects um, from a gene pool um, the most the most successful um, phenotypes are added to the gene pool multiple times, while the least successful ones are added less. Um, so it took a very long time for them to even um, learn how to spot the food. Um, but now we seem to have two main phenotypes, and it just hit 1 million. Just hit 1 million. So I'll just go through um, what I've noticed so far is that the two most successful phenotypes are as the spinning ones, which um, will are very good at zeroing in on food. However, they are very slow. You can watch this one in the bottom left corner. Not all of them are very good, but so it's gonna. Well, anyway, and then there are other ones which the ones that move faster. Um, they um, they tend to have tend to be not as good at locating food as the spinning ones, because the spinning ones are able to constantly update their field of vision in order to check for food around them, um, while the ones that move in straight lines or more straight lines, then they tend to have more limited inputs. Um, so waiting for a good one. Um, Okay, well you can see that one in the center just got some food at the towards the bottom, and it looks like it's zeroing in on the food below it, and it gets that food, and it might go to the right, and yep, it does. It's going to the right, got that food, and maybe it'll go up. Yep, it's going up. You can see it moving up to get that other piece of food. Oop, but I missed it. And it's coming back slowly. Alright. So part of the program, okay, here you can see in the top left corner, I have some stats here. Um, so as I said before, the each creature starts off with a health of 1,000. So after 1,000 steps, sorry, health of 100. But after 1,000 steps, that health reaches zero unless it can find food, and food will increase the amount of steps it can survive by 500. So obviously, the minimum number of steps that it takes for a creature to die is 1,000. So here we have the best, which is 12,000. So there was a creature, and I've actually saved it. Its genotype. I can reproduce it, duplicate it here in a second. But that one was really good, and it's consistently quite good. But unfortunately, it seems to have died out. Though there are traces of its genes in this in the gene pool. However, the average doesn't really reflect very well on how much evolution has taken place. So the average would indicate that on average, each creature is getting more than one piece of food, or between one and two pieces of food, or now it says, but it's a moving average, or it's a weighted exponential average. So the each new after each new individual another death occurs, that death um, accounts for 10% of the new average that's computed. So what I think the average is kind of useful for is in the earlier runs, when the steps earlier in the simulation, the average was well below 1,500. It was usually around less than 1,100 for the most part. Of course, it jumps sporadically whenever a successful individual appeared, but there weren't many of those back then. So um, now it's been, it's been pretty consistently above 1,500. And that sort of, I feel like the jump in the when the individuals learned how to zero in, that signified a big leap in their evolution. So I've saved that individual, the one that scored 12,000, and I can in this program I have a way to duplicate them. So if I can remember how to do that. Yeah, C for C and D for C. See there, this one. It just appeared, and it should be the same individual, though it looks like it's a bit confused because it can't find the food. Yeah, that's the problem. Some of them, when they can't find food, they don't do so well. There it goes. Zeroing in on it. They got the food, and then I'll probably head up into that corner to get more foods. Yep. And it gets that food. And that's... Ooh, which one's gonna get it? Not really sure which one's gonna get it. But anyway, you can see that one's pretty good. It's does pretty well. So let's I can also display the the genotype, which is encoded in the neural network. The neural network, by the way, is as I said, it's a total of what is it? 1, 2, 3, 4, 5, 6, 7, 8. 8? Yes. Or no, 6. I think it's. I don't know. It's, the inputs go into a hidden layer, and then the hidden layer is fed to the output neurons. But yeah, each piece of the DNA for the evolution is a value between -1 and 1 for that corresponds to the weights of the connections between the neurons. So this would be biologically analog of to axons and guys. That's pretty much it though. So I'm not sure how much more this will evolve. If I might add some more inputs, then could get some better results. Though it's doing okay, I think, given the amount of time. I mean, it takes a really long time for things like this to evolve. So, right, that's about it.